It's we'll get started for today. Oh, I need to put on the mic. Hello, 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 hello. So we'll conclude our discussion on optimization problems in the continuous domain. We discussed supervised learning, clustering, sorry, we'll be doing this today. Principal component analysis and matrix completion. And we were to complete low rank and non-negative matrix factorization. What I'll do is I'll just quickly run you through a recap of supervised learning, but this is extra optional slides presenting supervised learning from a slightly different perspective, which is basically a perspective on how lasso leads to sparsity. Because there was a question that some of you asked, how does that yield sparsity? Okay. So regularization is often used as a trick to give you generalizability, right? So you have this regularizer on W with some weight lambda, and W square, norm W square is often used. What happens if you replace norm W square with the one norm, right? So you can contrast the level curves. Okay, so I have this Colab notebook. Let me bring that up. I need this today. Okay, so in this Colab notebook, this is visible. Maybe I'll bring it. Okay. So this is a slightly different Colab notebook than what I showed last time, where the motivation for sparsity, how L1 leads to sparsity, has been brought out more explicitly. This talks about the probabilistic interpretation of linear regression to begin with, and basically how linear regression assumes Gaussian noise, right? The epsilon difference between the actual observation and the Y's has a Gaussian noise. Okay, so so Y is mx plus b plus epsilon, right? Okay, so this is visualization of what this Gaussian means. And now we have actually created some data which is linear plus some noise, which is actually Gaussian. Okay, and yeah, so we actually just plot the data and so on. But let's, and this is for classification task. We do the same thing for classification task, where you're getting data from a coin toss, Bernoulli trials. Okay, so now we talk about this prior distribution. This is a prior on the theta parameters on which you're trying to do maximum likelihood estimation, or map estimation, which is post data observation. How does the prior get affected? So the prior, this is the case of logistic regression. Okay, so now you have a prior, and then how does the prior affect the posterior? How does the data influence the prior to get to the posterior. From probabilistic interpretation. So this is, I mean, for different kinds of priors, we show how the posterior is affected. Okay. This is in the case of, yeah. So now let me get to, okay, this is what I wanted to show. So if you're trying to do linear regression, this is under different powers associated with the W, right? So norm W. Sorry, this is the data. I'm sorry, this is the data which has been obtained from uh, the same data, but you're now trying to fit regression curve with different polynomial functions. Okay, so this is polynomial function power 1, which means a linear function. Right? If you try and fit it using power 3, you get this. Now, without any L2, sorry, without any L1 regularization, you'll find that the curve becomes extremely wobbly as the power increases, right? As the capacity of your model increases, it reflects in its curvature. So the weights can also have very high magnitude. Okay. Now what we show is, okay, these are actual weights. So with model which is linear, you'll find that the well, we have one weight, most of them enhanced. But as you go to 50 in power, right, you'll find these model weights are actually very high. So what we do is we try and apply. Here you see we applied lambda. Okay, all of these are with lambda, but now we have a high degree polynomial. As lambda is increasing, you'll find that the curve is actually becoming kind of dumber. There's a lot of bias that lambda is brought in. So as lambda becomes high, especially with lambda equals 5, we find that the curves become completely dumb. It's high bias. It's not getting influenced by the data. So there's this typical bias variance trade-off. As you increase the bias, right, the variance would decrease. So you keep changing the data, you might not see as much change in the nature of the plot, the fit. Okay, and does it reflect on the weights? Indeed, it reflects on the weights. Okay, so you see that many weights are small. So this is with L2 regularization. Okay, so all this is with L2 regularization. The weights are becoming small, but they're not really becoming zeros. Okay. So if you have a loss function, okay, that's what we're observing here. L2 norm doesn't really drive these weights to zeros. You observe this? This is visible to everyone. So lambda equals 20. Unfortunately, the weights are all there, very small, but then they're not vanished. And this can be a problem, right? If you're trying to do very quick inference, a lot of the work on quantization. You've heard of quantization. If you're large language models, you're trying to quantize or compress the memory requirement for those weights. This is not acceptable. Okay, so what we do next? Okay, so this is L2 norm, and that's what I showed last time. L2 norm, the level curves are all these basically ellipsoids in dimensions. They could also look like concentric circles, right? But you could also add some conditioning matrix, right, AW, and make it look like an ellipsoid. But the L1 norm behaves like this, and I talked about the nature of corners that it actually attracts solutions. And let's empirically see that it happens. Okay, so now this is with L1 norm. L1 norm, you'll find that the curvature is even more restricted, okay, as lambda increases. So you would expect now the W to get sparser as well. Okay, let's see. Now we observe the weights and you find, oh, lots of the weights actually become zeros, perfect zeros. Okay. So one norm, the weights that were getting smaller start becoming exactly zeros. Okay, not all weights, several weights. Is this visible to everyone? The board is visible to everyone? Let me know if you want me to write on that white screen. I mean, it's going to require a lot of switching, so I'll use the white screen a little sparingly. Try write things on the board more often. Let me know if you want me to do otherwise. Okay, so this is an example of how L1 regularization not only helps you avoid overfitting, but also drives sparsity. But there is a trade-off, right? There's no free lunch. So the trade-off is obviously that you don't get what we call strong convexity last time. There's some nice properties that L2 gives you, which L1 doesn't give. More about that later. Okay, so this is what I wanted to show. Maybe I'll take a snapshot of this and put it out there so that you can register. This is what I was trying to show you. Okay. I'll put the link to the slides. You can go and navigate. Okay. Okay. So this is what I was talking about. You have an L1 norm. Now it turns out I talked about this posterior estimate. This is optional slide, so it's okay if you don't get all of this. But it turns out that it's a map estimate subject to a prior, which is called the Laplacian prior. Okay, so you have a Gaussian prior, basically what that leads you to L2 regularizer. So there's a Laplace prior which leads to L1 regularizer, and let's just plot Laplace and see how it looks like. Okay, so so you heard of the hare and the tortoise story, right? So it resurfaces. So the Gaussian is easier to estimate because it gives you closed form solution. But it's like what is it like? Hare. It just reaches a solution and gets close to a solution, probably takes a nap. But this Laplacian, it's like a tortoise, moves slower, but gives you sparse solutions. Okay, so this is how it peaks. This is the Laplacian prior, and you can see it kind of peaks very quickly at the 0. Depends on the parameters you set, the B parameter. So as your B reduces, you'll find that it peaks further. So this is another interpretation for sparsity. Okay, but then this requires a little bit more of probabilistic estimation, which is not the subject matter of our course. But since there was a question, I just thought I'll bring up this. Okay, yeah, and we'll talk about how we use the iterative soft thresholding algorithm to estimate parameters in the case of the lasso. And indeed, what it does is it thresholds. The algorithm by design thresholds. Very small values, it pushes them to 0. If it's close to 0 and it's very small in magnitude, it's pushed to 0 on both sides of the 0. Negative as well as positive are pushed to 0. Okay, so this hopefully gives you an idea. That's the same thing I was trying to show you. Many of these are, so if they are less than some value, right? So if they are less than some minus eta lambda or greater than lambda, sorry, if they are less than eta lambda or greater than minus eta lambda, in those cases, you'll find that they have actually all been pushed to zero. Okay, you got some better understanding. So the second thing I just want to recap, we talked about principal component analysis. So this is again, uh, you know, uh, it's just an application of what's called Occam's razor. All things being equal, pick the simplest solution. Okay. What principal component analysis builds on this simplest solution idea, right? Why is simple better? So principal component analysis says, well, if you're going to compress the data, pick those directions which explain the maximum spread of the data points. So that is simplifying, right? I gave this example of trying to compress information about all the classrooms here. And what would help you compress information? Well, if something that largely characterizes all the classroom, that's a simple explanation. Somebody comes and says, oh, sorry, all of the walls are blue. Simplistic explanation. That's what lecture hall complex is, right? Most of the walls are dark blue here, probably. But when you go to PC Saxena or other places, they're not dark blue. This is a very simplistic um, explanation. That's what Occam Razor does, and that's what BCA builds upon. So that's what we saw, right? And basically, you take the um, top k singular values, right, from the eigen decomposition. That was the algorithm, right? Which leads to minimization of this objective, or it attempts to minimize this objective, the reconstruction loss. Most of what we see today in whether it's autoencoders or diffusion models, they're all trying to do reconstruction. And diffusion models do reconstruction. Okay, so there's some extra optional slides. You can go through it, but I just wanted to give some pictorial depiction. So idea, if you recall, was you're taking your points x, projecting them to z. So somebody was asking why there's a u transpose xi, right? So if u is your compressor, then u transpose is how you apply it. Okay. So this is a compressor, u applied through a transpose, and this is u transpose, which is a decompressor, again applied through a transpose. Okay. So typically you apply these through a transpose. So yeah, that's one perspective, error reduction perspective. Go from x using u transpose to the encoder or the compressor, and then you have a decoder which takes the transpose of the u transpose and recovers back the x. This is one perspective. And this is courtesy this nice book, Mathematics for Machine Learning. You can have a look at it. There's another perspective which is maximizing the variance of the projected data, which I didn't explain in the class, but I gave a hint. I told you about points which were uncorrelated being uncorrelated post the transformation, and that's pretty much what it says. So so objective here basically is that in expectation you want to minimize u transpose x norm square, which is basically the variance. Okay, so you want to capture the direction of maximum spread. It's like finding the direction with maximum variance. Okay, since this is optional, I'm just running through it. This is what I've shown you in the last class. Right? This is the first principal component, direction of maximum variance. The second one, you eliminate that direction and then find the next direction of maximum spread. That's how you run through this iteratively. Okay, so I've just run through how the first principal component algorithmically is maximizing variance of the projected data. And I didn't show these examples, but you can look at, if you just take the first principal component, it's like capturing most of the information about the aids. Like this is the original data. And the first principal component gives you a fair idea of the aids, but it's very hazy. Right? The edges are blurred. And that's where if you take more principal components, the blurring effect will all start vanishing. Same thing with faces, right? If you look at different faces, then you'll find that the first principal component might help you preserve the most of the features in the face. You find that, right? But the details are being missed out. But it's a face. right? If you go by first principal component directly, you wouldn't even know that it's a phase. Maybe it starts looking like, right, your chapati. The impression of phase does come through the first principal component. Okay, so there's a PC algorithm which, by the way, now somebody may say, what if we want to deal with non-linearity? Like I talked about polynomials in the case of doing regression. What if I really want to do non-linearity, and especially non-linearity in very high dimensional spaces? So there's an entire area of kernel PCA. Absolutely, if you don't understand, it's okay. But all it says is, instead of representing points explicitly in a feature space, if you could just compute pairwise similarities of points using the kernel function, right? Which could be e raised to. So kernel function could look like e raised to minus of sigma times norm of x1 minus x2 square. Basically, an infinite dimensional representation of x in an implicit space. But kernel PCA can also work there. And thanks to a lot of the math that I talked about. Okay. So kernel PCA can also be solved. Now let's go back. I'm just recapping. So given observations y1, yn such that each yj, ajx, right? Aj is, for example, the cost of an element. So single element or a combination of elements. We saw that you can actually solve using iterative single value thresholding. Okay. This is what we saw for matrix completion. Now we said, well, we want this x to be simple. Is there a way we can put a constraint on simple in a different way? So one constraint for x was what? What is the constraint we discussed last time? This was our fourth application. So part one is what we did in the last class. Part one, which is x simple. It's like saying x has low rank, and which is approximately the same as low sum of low sum of singular values. This is low UPL. Right? But there's another part two. The part two, which says, well, what if I take my x to be L times R, right? And let's say L is an n cross k. Dimension m cross k, m cross k, and R is k cross k. By design, what will be the rank of x? X is L into R, L is cross k, L is k cross k. What will be the rank of x? Cannot exceed, right? It means that the rank of x has to be equal. So can we make use of this property? That's it. This is our application. Now I just call it a new application because this has applications beyond matrix completion. So it's really interested in say low rank matrix completion. For many other problems, not this one. That's why I said I'm building upon my previous use case. So what would you do in this case? What will be your next step? I can apply it for say the same problem of matrix completion. I can you have another objective function. So now we are little agnostic to objective function, but I'll just take the same objective function as last time. What is the objective function? You should now start recapping. This is important. What was the objective function we had then? Huh. So you can take a very simple. I what we took then was yj minus some a times x, right? But you can so this x will be basically allowed. X is now going to be replaced with LR. But instead of this, I could also consider a simpler problem where I say, oh, I just want to minimize some x theta. What is what I've observed, right? Minus LR on all the observed entities. Wherever you have observed, you should match. That's the earlier objective. This is the more general objective. I just said wherever I have observed data, x delta observed, I should match those indices in LR as well as possible. There's some overall observed. Is it visible? Is it visible? Okay. So something of this. Will we need matrix regularization again? Earlier we have all this, right? In part one, we want low rank. So we had to explicitly put a nuclear norm. Do we need that here? We have to add this, right? Plus lambda whatever. In laws. Plus lambda. Do we need that here? No, right? Now it's possible that you may want some rank constraint on L and R. That is possible. Is this visible? So there are multiple possibilities. One is have low rank. But that's typically not the case. We come to that. One possibility is requiring to have low ranks. So even if you have required them to have low ranks, uh, go back to your collab notebook, the last week's collab notebook. Friday. Remember this collaborative talked about. Right? If I had to put some constraint on the right, how would I do that? let me give another example of a constraint. So let's say I have a constraint that both L and R must be non-negative. Non-negative. So in addition, let's say I want L and R to have non-negative entries. Could I do something interesting? How would I modify my approach from last week to make sure that L and R have non-negative entries? Right? Or coming back to this, let's say I wanted my W's and V's in linear regression to be positive, non-negative. What's your intuition? What does your intuition say? How would you impose that? I have an iterative algorithm, and suddenly I want that entries should be non-negative. What would I do? What comes to your mind? Huh? Huh? What would you do? Operationally, huh? Tell you, but you're saying you just flip. If anything is negative, set it to 0. Right? Project. You're saying anything that is negative, project it. Huh? So, or in this case, if I had put that constraint here, so somebody was saying hinge law. I'll take this W being U and set it to this plus. Simple thing, plus. Right? That's the general idea. Projection. So what would I do in my case? For non-negative entries, I take N equals L whole plus. It means, to understand what plus is doing, set negative entries to 0. R is equal to, similarly, R whole plus. Okay. So obviously the question will be, okay, how do you then determine the R and L's? So the idea is not very different from PCA and matrix completion, iterative algorithms. So let's take this matrix factorization optimization problem. And now I want to develop the entire, I've taken the same loss as last class. So as matrix completion, but under this LR proposition. So I want to add these non-negativity constraints, which I talked about just now. So that the entries become all non-negative at every equations. We know LR is that L greater than equal to U, R greater than equal to entry ones. And all they're doing is add this projection step. Right? So it turns out that the projection, while I said flip it to 0, For it to have good convergence properties is not sufficient. You should also do some rescaling. Basically, it's like saying if I set some of them to 0, right, then I have to also proportionately reassign the weights so that collectively the norms are maintained. Understand? So the only addition I'm now saying is, well, it's not just projection with rescaling. Projection basically means rescaling. And we have always this experience, right? If you project from 3-dimensional space to 2-dimensional space, based on the angle at which you're projecting, there'll be rescaling. The object doesn't look the same. It's not just clipping. But if you're doing a complete sagittal or axial view, yeah, thresholding is a trivial way of projecting, but not always. Right? So there's some Clarus-Kuntakar conditions that are required. So there's some rescaling is required. Okay? So here is the iterative projection algorithm. So what we are doing here is L0 R0, like in the case of matrix completion. And then this is the rescaling effort. LTIJ, RTIJ, both of them are obtained as this is for the non-negative ones. Even for the non-negative ones, you are taking the old ones, LT minus 1 IJ, but rescaled based on the the previous iterates, the magnitudes of the previous iterates. So why do you rescale? So that the overall mass that I have is not changing across iterations. What might happen otherwise? What if I don't rescale? Anyone? Any guesses? But I mean, let's think about it from an implementation perspective. You implement it. You keep clipping values to values if they're negative. And the rest you just use your standard iterative procedure. What do you think might happen? Sorry? It may confuse. Okay. What else is possible? Sorry? You think some of the weights may start just going to 0, declining altogether? Okay, so some of the weights might just start, but you may have to upscale weights that are going very slow, right? And downscale weights which are becoming very high. Even from a stability perspective, scaling might make sense. Okay, so this is the iterative projection. It's an iterative algorithm, but it's a projection algorithm. You can also add a nuclear norm constraint for LNR. You want LNR to also have low rank constraint. Okay, so I think you got a flavor of some of these algorithms now. Now I'll talk about some more optimization problems without an idea of the algorithm. So this algorithm just gives you now whatever I explained so far should give you a spectrum of the possible right design choices we have, what we anticipate in the code. And sometimes y is fully observed and we want a non-negative low rank factorization of y. This will be this is when y is fully observed. The observation which I talked about might be that actually you have already observed all the data. You still want a low rank non-negative factorization. Okay, clustering should be very intuitive. And it's another application of or instance of unsupervised learning. But there's an interesting aspect about clustering. Now we are getting into, in fact, with the last two applications, we are no longer purely in the continuous optimization space. Why would you think so? I've dropped the hint. Clustering is no longer necessarily continuous. Why? So I said continuous relaxation. Okay, so let's say I have these data points x1, x2, xn, right? And I want to, again, simplicity is something I brought up earlier. So I'll say I want some simplification, so the clusters to look simple. How do I impose that? One notion of simplicity is that each cluster has some mean ui. Each data point j belongs to one of those clusters. Pij is 0, 1. It's a membership. Okay. So clustering configurations. One is Pij membership point xj cluster I cluster. Keep the parameter point. Okay, so what could Pij be? It could be 0, exactly 0 or 1. That's one notion of simplicity. Which means every point either belongs to a cluster or doesn't belong to a cluster. Any other notion of simplicity you can think of? What is the part? I have one more part in yellow highlighted, right? What is that saying? So another simplicity is that Pij is between 0, Pij is real value between 0 and 1. But for all the clusters that a point can belong to, summation over I, the Pij should be 1. Which means a point should have membership that sums to 1 across all the clusters. Membership sums to 1. Okay, this one was basically binary membership. So this is one way of simplifying, other way of simplifying. And our objective is to ensure that the sum of the point j with associated membership I, Pij to cluster I brings you as close as possible to the mean parameter of that cluster I. And our goal is to find the min across all possible Pij. So Pij could come either from 1 or 2. You could have also more options. What are other options? We want the mu's to be far away. By the way, is 1 sufficient or you need 1 plus 2? 2 can exist by itself, but don't you need one more constraint here? Pij's are 0, 1 with the additional constraint that. So you want the point either belongs or doesn't belong, but it should belong to exactly. So this constraint needs to be completed, right? Here also we need a We need a constraint that summation over I of Pij is 1. So I've used this keyword soft K means, right? This is soft. This is an example of soft K means. And this is hard K means. So the goal is basically to find these clusters, Pi with cluster consisting of similar instances. Such that each of the points is basically assigned to, in this case, exactly one cluster, case 1, and case 2 assigned to multiple clusters with its membership summing to 1. So this is, so if you want membership piece as a data is partition, you would go for option 1. Right? In option 1, RK means you partition the data. That's what we are showing here. So now, which of these is a discrete optimization problem? Yes. Okay, so 1 is a discrete optimization problem. RK means. Is it only a discrete optimization problem? 1. Was this visible? No. No, it's not visible. So there is discrete PIJs. That is either 0 to 1. But is it through and through discrete? The question. Are we only trying to minimize with respect to Pij? Have you missed out something in the objective? You want to minimize with respect to Pij as alone or something else? As well? Mu wise also, right? You want to find the cluster center C. You want to do the following. You want to assign a green point to this cluster and also evolve the notion of the cluster itself. Right? Now, the moment the cluster changes, some other points may have to get reassigned. Likewise, this red point, it's assigned to this cluster, and now it's changing the meaning of a cluster. So it cannot be only, so you may have a distance xj to mu I, right? So why you are trying to find the minimum, the closest cluster for xj, once you assign xj to the cluster I, the cluster has changed. Mu j may no longer be its mean. So what is the actual objective? It's been over Pij and all the mu i's. Now with this, is it discrete only? Are the mu i's only discrete value? We had discrete Pij, but continuous mu i's. So first exposure to a problem is mixed, discrete, and continuous. It's discrete plus continuous. Soft K means what kind of problem is it? The hard K means says that you need a membership key so that data is partitioned. That's what we are showing. Pij will be discrete plus continuous, right? So the soft K means what does it say? So this is the right. This is a example of hard K means where each point x belongs to one of those clusters. And you're trying to find a point, the cluster to which a point should be belonging, and evolve the notion of a cluster. So this is hard K means. But in soft K means, what happens? Because you have Pij's continuous value coming to one constraint under that constraint. Ui's are also continuous. So it's a completely continuous optimization. Okay. This problem is a joint discrete and continuous problem. What I've shown the board is completely here. On the slides is the mixed discrete continuous hard K means. What I've written on the board is more general form, which can also be soft K means. Okay. Any questions on clustering? We'll see more of clustering, the discrete case. For example, if I want the mui's or the cluster centers to coincide with points, you'll find that is a completely discrete optimization. We'll do that later. Let's take one last example of continuous optimization, which again borders on discrete optimization. Okay, and this is related to RLHF. What is RLHF? Reinforcement learning using human feedback. Right? So I'll give you an idea of how this problem is related to RLHF. Contextual bandits learning from log data. So let's say there are K ads which you want to show to users. Or you want to, instead of ads, you may say, I want to apply some treatment to a patient. Right? Now how do you determine the ad to be shown to a user? There's some policy. A policy determines, okay, which this ad should be shown to this user. Or there's some hospital policy, some guidelines which determine what treatment should be given to what patient. Now it's very important to be data driven here. A lot of the large language modeling, RLHF, is very data driven, right? So you've seen conversations with ChatGPT or your own fine-tuned model. It does evolve as you converse, right? What happens if you don't converse? Okay, there's something called the Simpsons paradox. I'm going to show you that right now. It's a nice applet. Show the Simpsons paradox. This is this one. Can you see this? So what you see in this applet is as follows. Reset data. So you have men and you have women, and then you have treatment protocols A and B. And you can see, well, for treatment protocol A, how many survive, and you can look at the percentage of survival. Okay. And what this is showing is, if you have an ad hoc policy, right? You see this curve here. Basically, you can. Yes, in this, you can slide this. Okay. What you see here is based on some policy. Okay, certain number of men are given a particular treatment. Certain percentage of women are given certain treatment. Look at men. The percentage surviving, as per percentage surviving, A is 60, and for women it is 95 in under A. So what's the impression you will get? What's your overall impression? Treatment A, protocol A is better or B is better? But the interesting thing is if you combine both of these, look at the percentage surviving. What is better? B is better, right? To understand the paradox, as per individual men and women analysis, A seems to be better. Combine them, B is better. I'll explain this in a little bit more detail. Now you can do the following. You can I can go and change the slider. I just go and change the slider. Now what has happened? If I change certain policy, then what has happened? So I have some underlying policy based on which I assign, right? Then what has happened? Both for men and women, A is better, and overall also A is better. So the paradox is not there. Paradox is where the individual subpopulations show disagreement with the overall population. So what we want to do? See, this is the problem, right? If you give ChatGPT the same instance to everyone without any fine tuning, it's possible that there's a paradox. Its thinking is recommending nicely to everyone. I'll give more examples. But overall, people are unhappy, right? So, without delving more into this applet, let's get into some more detail. So, how can you pose an optimization problem in the context of this paradox and in order to learn the right recommendation policy? We want to be data driven. That's what I'm trying to impress. You cannot be doing trial and error. You need to be data driven. And let's see how we can be data driven. Is this problem clear? Application number 6 or 5. So what is going to be the log data like? So you'll have people come in, individuals, as we saw in that. Right? For each of those individuals, some action may be taken. Action, what was action being taken there? Certain people were given treatment protocol A, some were given treatment protocol B. Or if it's movie ad or whatever ads, will show ad A to one person, ad B to one person. So you have XI, you have AI, the action that the agent takes. But what happens? What's the reward? In the case of the this operation, the treatment. What was the reward like? Some implicit action policy took action, but then the reward is basically how many people survive. Right? It could be survival, it could be something else, it could be RI. Okay. Action was taken. Now this action was taken based on some propensity that the model had. Right? Somehow that slider I showed you is like a propensity. What percentage should be given? Of women should be given a particular treatment, what percentage of men should be given a particular treatment. That's something called P, propensity. This is the kind of log data we have. I'm going to the next few slides run through this a little more carefully. Okay, so here you want to learn from contextual bandit data. I'm now taking ad example instead of I mean that's very sad to see, survival rates changing with people. So let's take a less depressing example. So you have title, of an ad. So features, right? Features, title, ad, query, etc. Those are all features of the ad. That's XI. And oh, sorry, that's XI. Sorry, for individual of an individual. Take an individual. Now, given an online policy which basically says that now we have taken a slightly different example. Let's delve into the example. So what it has done is say, okay, males and females, and the two types of ads, sports and movies. So what we show in this matrix is if males are shown sports, what is the kind of reward they give? So they give 0.4. If females are shown sports, they give 0.8. But in general, females give higher rewards as per this data. For movies, also they give 0.7. So relatively, they give higher weightage to both sports and movies, but within the sports and movies, they are preferring more of sports. And males give low weightage, but relatively higher again for the sports arm. Okay, so this is what we call as reward. This is a reward. This is a feedback. Now let's say, okay, so this is a let me explain the overall context. Here you have X, to which there's an action taken by the agent. Action is choice based on X, the input, and parameter theta using some policy phi theta. Our whole goal is to drive phi theta using data. So this AI came from this result of policy phi theta our goal to learn theta, which means to learn phi theta in a data driven. So what is the data? For X, action A was taken. So action was taken. Action AK based on the X and parameter theta is equal to phi theta. And then the user may click, may express happiness or some level of distress using a reward. This is an example of a reward. Right? And now I want to revise my phi. But there is one more point which I talked about. This is the propensity. Okay. So we are given bandit log data in the form of xi, x1, a1, r1, p1, x2, a2, r2, and so on. Now, propensity. That propensity was what I was trying to show in the Simpson's paradox applet. But I brought it up here. Little bit more on propensity. I'll use that. Let's set the pole. And let's take this one example. Right? So, PA, that's in pink color. So, let me try and highlight this in pink. So, what is the propensity? It's saying that, well, I can assume that men should be more fond of sports, right? And women should be more fond of movies. There's a bias. So clearly a bias in my head or in the head of the agent. So that 0.75 is the propensity, but for males. But that 0.75 to 0.4, right? And 0.3 into 0.25. That's the total weightage for sports and movies respectively for males. Now, if I add up for sports from the females and the males, what do I get? 0.5. Okay. So, what is happening here is P sports males into that's the first. reward that a male gives to sport into the propensity of the model or agent to give show to males sports, plus reward that a female may give to sports into propensity of the model to show sports to females. This is exactly what is point 5. But unfortunately, this point 5 is less than the other, which is rewards that the male would ascribe to movies. This is B for movies. Into propensity that male would ascribe to movies, plus the reward that female would ascribe to movies, into propensity that females would ascribe to the propensity of the model. This is point. So point 6. Now this is counterintuitive, right? Overall, exactly what applet should. This is the Simpson's paradox. So propensity can be a spoil sport, right? This propensity can be the spoil sport, and we want to guard against that. The bias that the model is carrying. So how do I design an objective function that has guardrails against this propensity and that can learn from data? So assume we can take a fixed number of actions. What do I do? AI is showing sport ad, A2 is showing movies ad. There are 2 actions in this case. X1 to Xk are the feature vectors associated with K actions. And AI is the action chosen by the current online policy. So what's my goal? My goal is have the model predicted argmax action for each input I, match the action for which the user assigns the highest reward. Can you try and write this objective? Try and write down this objective. We have given you enough background. Okay, there's one more point. Should account for, which I already mentioned, probability of the logged action by the current online policy, the propensity. PI is also important. The current model has some propensity, so that also we need to account for. So debias the model from propensity. So what will be your objective? Try and write down. You need to discount for that propensity PI. Right? If you keep going by the propensity, you may actually not learn as much from the data. So you have to discount for that propensity. The model knows its probability. It's bias. You have a conversational bot built on top of a pre-trained large language model, can calibrate what's the probability of emitting a sequence of words as against some other sequence of words. That's a propensity. It already has. And you guys might have seen all kinds of strange things happening at times with these large language models. The bias that creeps in. So if you want some help, what is action AK? Action AK will be argmax as per the pi theta policy of or the probability of, or maybe I should use to bring it up, but some function. If there's a function f, it is going to be, which is just the likelihood of ai, then ak ai comma x. Something like this. You need a function f. So phi is just a policy, but the policy is based on some function. Right? So you need a function f to be able to complete the story. You have also the reward. Reward Ri obtained by choosing action ai. And then you need a function f as well. Is the what I showed earlier was the reward function. And we'll define our policy phi theta as argmax over j equals 1 to k of x theta x j. Now you should be able to complete. That action which maximizes the function. X itself is vector corresponding to different possible actions. For each action, what is the orientation as per its core features? Anyone who come up with it? If I want to discount propensity, what would I do? So if I want something to be dampened, what would I do? You would scalar multiplication. No, scalar multiplication. Would you divide, multiply? Okay. So if you want to minimize, you would try and multiply. If you want to maximize, you would try and divide. Right? So dampen. Okay, so R should have a dampening effect or scaling effect. Reward. Scaling effect. Right? So can you have something which is a function of R divided by P? So hint number one. Right? For I, can there be Ri divided by Pi? That's how it is. Ri divided by Pi. Into what? Into something that will look at whether the predicted action for I coincides with what? Coincides with the chosen action. So I predict a movie to a person. Did the person actually like movie? Was that as per the ground rule? Right? So AI, did it agree with the policy phi theta? Phi theta given action. Did it agree with AI? So AI is what I observed. Phi theta is what the model gave. Right? So this should be very simple, right? I want to find a theta. So let's try and write down our first question. And you should tell me what is the problem. So theta star is Rmax for all theta of. You can also tell me whether it should be a summation or a product. Reward divided by density of some indicator function, or I can just put it like this: phi theta xi equals kx. whether pi theta xi match AI. Pi theta itself is based on argmax of f, right? And an example, a simple example of f theta would be just a linear function. Yeah, but theta itself will be indexed by action. So for each theta is a vector, xi is a vector, featureized as per different actions. You are looking at that component of xi, that action where this peaks. So this is 1, 2. Is there a problem with this problem? How do you initialize the pi thetas so that they don't drift away from the AIs altogether? And you keep recommending, right, as per your bias, models so poorly initialized. The user keeps on clicking, never learn, people leave your system or conversational bond. That's true. In fact, that was a problem in many of the previous GPT models, right? They were very bad. So thanks to large data, now the initialization of these models is much. So that's the whole advantage of pre-trained models today, right? They initialize with very good parameters, and therefore they are learnable at least. So very good point. I mean, but let's assume that is so that's a challenge. Let's. This is my first formulation. But there are other issues also. The rewards are assumed to be non-zero. I may choose an action but not give any reward. Obviously, that's why RLHF mechanisms are there, so that people actually give rewards, right? If you are conversing, you may not. You've seen ChatGPT put a thumbs up, thumbs down, right? But if you don't do it that at all, the poor model doesn't learn anything. You need an explicit, agents who are trained to sit and give feedback, rewards to the model. That's one issue. Or one challenge. So now, no explicit indication of the type of the input. Input type was to be handled by the black box featureizer, which means that now we have not gotten into the details of the XI itself. This somebody may wonder, right? What is happening in the XI, right? XI is basically a list of all possible feature action pairs. Can this be a little bit more complex? Can this be itself demystified? So all that has been left as a black box. Right? That's another issue. And the other thing is, entire log is considered to be a one monolithic set. But there could be a temporal aspect. It has been evolving over time. What mattered 10 years back probably doesn't matter now. Or what mattered 1 month back probably doesn't matter. Right? And this propensity, in the case of RLHF, as I said, could be the probability of a fine-tuned model. And could the human reward could be the human feedback. Case of RLHF. But yes, these are some limitations. But there's one more limitation. What is that? This objective isn't continuous at all. I have put an indicator function, right? Equal to. So what would be your natural instinct to make it continuous? Softmax. Right? So instead of putting an indicator function, you find the logic associated with AJ. That's the next step, right? Softmax relaxation. So we just replace this indicator with the probability as far as softmax. This is what we did for logistics earlier. We do the same. But f remains my simple linear function, or my link function. It could be non-linear as well. Got an idea? Okay. Okay, so this kind of brings us to the conclusion of several continuous optimization problems. Now we just get started with some discrete optimization problem. We'll do one today. It will not take so long. And we have got a flavor of. See, already you saw that contextual bandits and clustering had a flavor of discrete optimization as well. But let's look at purely discrete optimization problems now. Okay, so let's say as a sentence, today is Tuesday, the 16th of January, 2024. And I want to parse this sentence, right? Find part of speech tags. You know what are part of speech tags? So today would be a noun, is would be auxiliary verb, Tuesday is a noun, proper noun, the is an determiner, and so on, right? I may not want to just do a part of speech tagging. I might want to find what is the structure of the sentence itself. So I'll give an example here. Sorry. Here. So let's say there's a parse tree. You can go to core.nlp.run and generate your own parse tree. So this is the entire sentence. Today is Tuesday, the 16th of January 2024. Then there is a substructure in this parse tree. Today is Tuesday, which is a kind of independent sentence or substructure to a sentence, which I could club with many other possible subphrases, right? Phrases. This is called a noun phrase followed by verb phrase. You can see this S, which is sentence. It's a part of a sentence. The 16th of January 2024 again is a noun phrase, which itself consists of the 16th of January as another noun phrase. Right? Of January itself is something called a prepositional phrase. Of something. Okay, so this entails finding multiple possible such parse trees, right? And determining that parse tree whose probability is the maximum. So pretty much every time you do generation, right, in ChatGPT, in large language models, you have to do this kind of decoding. Either find the right word, or given the sentence, find a parse tree, or given a sentence, find what to respond. So it is all discrete optimization, right? So the search is over a very large space of discrete outputs. Or let's take the more classical Ising model. What Ising model will do is will look at electron spins. What you see here is electron spins. 0 would probably mean up, down, and 1 would mean up. So you need a stable configuration in a lattice. Stable would mean energy should be low. So what is the configuration that makes it low? Obviously, you can't have everything going up. Right? That would be very high energy. So again, coming up with minimizing an X configuration, this X, so that it minimizes the energy. Right? Or I take a simpler example, which is part of speech tagging here. So let's say a verb, verb, verb. So you can see there's a stack. Right? So what I'm showing is all the possibilities here for this sentence. For any sentence, today's Tuesday, the 16th of January. So Tuesday is a weekday. 16th is a number. January is a month. And 2024 is a year. So I've gone beyond part of speech tagging to something called named entity recognition. Right? So the right configuration is the one in yellow, right? Tuesday is a week. Tuesday could have been someone's name. Tuesday could have been an organization's name. Likewise, 16 could have been something else, 16th floor, or 16 could also be some named entity, some entity's name, and so on. Right? 2024 could have been some other quantity, need not be a year. Could be the weight of an elephant, right? So, but then the context tells you that this is the right interpretation: week, num, month, year. So what you're doing is you have range of possibilities. Find that path L1, L2, L3, L4 that again minimizes energy or maximizes likelihood. So these are examples of discrete optimization problems. So for effective date extraction or annotation, you would like the configuration highlighted in yellow, this configuration, to have lower energy or higher likelihood than any other configuration. So of course, this learning I have to learn so that the model predicts this high on high energy, is it low energy or high likelihood configuration. So most discrete optimization problem has some element of continuous optimization. We saw that already with clustering. But still, the inference problem is a pure discrete optimization. Right? So what I do is I'll take some of the examples in the next class. What I want you to do also, I want to spell out, just please hold on. So I'll take some of these examples, but there's some reading I'm going to give you. So you have to just ensure that you're kind of comfortable with vectors, matrices, because now we'll do many of the foundational aspects a little fast. So what is the notion of matrix vector product? We have already used matrix vector products so many times, but this is going to come up even more often now. So please go through this. No, just get familiar with matrix products, and then derivatives. We're going to use derivatives extensively. I'm going to give you some of these examples, and last year's answer also there. Okay. So, for example, if you have y equals max of x comma 0, what will its derivative look like? So, I'll be talking about something called subgradients later. But for now, in single variable calculus, you should recap. I'll give some examples of partial derivatives here. Again, brush up partial derivatives, please. Okay. And the notion of a gradient, which is basically a vector of all the partial derivatives. Okay. So please brush this up. Hessian of a function is nothing but the matrix of all mixed partial derivatives. X1, X2, X2, X3. Okay. So get familiar with this. So I'll give you some examples for W1 square by W2. You should be able to compute its Hessian. And then I'm going to see all the losses we have discussed so far. Try and compute their gradient. Please do this. It'll give you, it'll make a world of difference. You may think you know it, but just write it down. But I'm not going to derive all of this in the class. So you should try and write the compute the gradients of those losses. Then you can also try computing the Hessian, which is the matrix of its partial derivative. Okay, so try doing these because what we'll do in the next class is build upon this, run through some basics of optimization from the perspective of calculus. Okay. So that's a homework for you. I'm going to leave homework hereafter in every class. So today is a significant homework. I'll conclude the discussion on discrete optimization problems and then really plunge, assuming you have done this background reading. Slides are all there. I've also put in some of my background lecture notes on metrics, like matrices and linear algebra. You might find that helpful. Thanks.